Okay, thank you, Nico. Thank you for coming. So what I'm going to do is I'm going to talk about Nymote, which is a software stack we're trying to build, and in particular, I'm going to focus on MIRAGE OS, which is kind of the core component of this, and the technology on which we're building all the other pieces. There's a lot of people who have been involved in this work, by no means just myself. Anil Madhavapedi in particular kind of leads this project. And then there's a cast of, well, tens at least, who've been contributing. And quite a growing open source community around it as well. So if you're interested in taking part in this and kind of joining the push, then there's some links at the end of the presentation. Sign up to the mailing list, pull the code, and see what you can do with it. Just before I start, can I just ask, has anybody here tried Mirage? Out. One. OK. Well, good. More should. It's really good. So I'm going to talk about Mirage. In particular, this is most of this is the current version is 2. We're just releasing 2.5 currently. If I had been a bit smarter and in less of a rush, I would have remembered to bring with me the QB board that the photo is taken of, and you would see the slides that I'm presenting being hosted off that. But because I didn't, I'm currently hosting the slides using the development version on the laptop. But if you go to our website, dex.openmirage.org, the same slides are also hosted there. And these are all being hosted as a Mirage unikernel. I'll talk a bit more about what unikernels mean during the presentation. Serving up the content as a single compiled OCaml image running on Zen. I'll go through all that in a bit. But to give the context, some more of the details of the context there, the slides were written using Mirage on this laptop. The preceding picture showed them being hosted in a 2.5 megabyte Zen unikernel. So this is a virtual machine running on Zen. Is everybody familiar with Zen, by the way? Is anybody not familiar with Zen? Yeah? And so if I use terms like virtual machine, that's all OK. Good. Just checking. Right. So 2.5 meg Zen unikernel, which does not contain any Linux. Right? There's no separate operating system there. This is the application booted directly on Zen. Written in statically type-safe OCaml, including all the device drivers and the network stack that's necessary. When you include all the content of the slides encoded in an OCaml string, it's about 7 megs. The application logic is then just a couple of source files, and everything else is sort of filled in during the compile and link process to provide all the necessary underlying technology that the application expects to sit above. One of the nice things about this is the binaries are small enough that they can be tracked explicitly. The compiled output can be tracked explicitly through Git. And I'll talk a bit more about that at the end. To give an idea of the spec of the platform running on, so obviously standard kind of big x86 Zen style servers. But thanks to the support now for Zen ARM, we can also run on these kind of devices. So the photo was a QB board 2. It's about a 55, 60 euro board, I guess, so fairly cheap ARM-based platform. So I'm going to talk about first why unikernels and try and motivate this a little bit. There's a sort of generally accepted wisdom that it's good programming practice to use modularity, focus on compositionality, to break things down into smaller pieces and be able to assemble and recompose them back together again. We tend not to do this when we build distributed systems. So why? Well, our claim would be that traditional systems programming tends to involve building services for a single environment. So you build a service to run on a server, or you build code to run on a client, or maybe you build code to run on an embedded device. You tend not to build code that's going to run on all of these different platforms sort of uniformly. But nowadays, we're starting to see more and more heterogeneity in terms of the platforms that people are trying to build code for. So cloud services with all the problems of flash crowds and so on, smartphone programming, JavaScript apps being built to run in browsers, Internet of Things devices coming along with very tiny processors, much more embedded style of development, even kernel modules to extend system functionality. And it's quite difficult to reuse the code between these platforms. So once you get it right on one platform, you start from scratch on a different platform. This is kind of seems a bit wasteful. And our claim would be this is going to get worse and worse and worse, right? With more and more IoT devices coming out, different platforms, user space libraries, very dumb kind of stacks, constrained programming environments. It's going to be difficult to keep these things running correctly. There are a couple of seats at the front, by the way, if you want to come and sit down. People always fear the front. And there are more and more examples of situations where this is causing a problem. So still relatively recent, problems of security vulnerabilities, significant security vulnerabilities, and quite important pieces of software. I think this morning there's another 7 vulnerabilities in OpenSSL that have been announced. I think 6 were moderate, 1 was low priority. So there's more, there's an ongoing stream of these kind of security vulnerabilities being detected and having to be fixed. And they're happening in quite important, quite key pieces of the software stack that we use. Our claim would be that one of the fundamental problems that underlies all this is the complexity that you have to deal with when you write this kind of code. So applications and frameworks get really deeply intertwined with the system APIs that they sit upon. And it's difficult, therefore, to port sort of reliable, known to be good code to different platforms. You have to work quite hard to get this kind of platform independence in some of these libraries, particularly system-level libraries. Another source of complexity is that current operating systems sort of derive from a notion that you want to offer dynamic support for multiple users to use a single machine and to be able to run multiple applications simultaneously. So you've got lots of ability for applications to be running which are going to interfere with each other. Okay? And this offers a lot of scope for uncontrolled interactions. So you can choose different operating systems. You can choose different distributions for your operating system, different versions of those distributions, different versions of your libc, different versions of OpenSSL, different versions of all these other system libraries. And you need to make sure that the set of things that you're using is going to work well together. And you need to remember to upgrade the things where vulnerabilities are discovered. You need to remember to manage those deployments. It gets even worse when you think about how application configuration fits into this. So you have files being put under /etc on a Unix system, or you have things being put in the registry on Windows. You have application configurations, you have dynamic application configurations, so maybe dynamic firewall rules because somebody goes and tweaks something, versus the static firewall configuration that happens at machine boot. So there's lots and lots of sources of complexity, lots and lots of things that can interfere with each other, and it's kind of difficult to manage this system. So this leads to lots of pain points. It's complex configuration management. Duplicated functionality leads to inefficiencies. So when you have a hypervisor, typically on top of that, you have an operating system. On top of that, you may have some kind of Java virtual machine or something. You'll have a lot of system platform libraries. There's lots of these things are all trying to provide things like isolation, resource management, and the other features an OS would provide. The images that you build and boot on these things tend to be quite large. So that leads to quite long boot times. And there's just lots and lots of code involved. I mean, just many, many lines of code involved in Linux through Java and all the rest of it. So this means quite a large attack surface as well. So there's lots of points in this system where we've ended up in a situation which is perhaps not as optimal as it could be. I'm being polite. A common approach nowadays to deal with this has been to technology like Docker, so containerization. The idea that you want to bundle up some of this state and be able to treat it as a single thing and manage it as a single thing. And I guess so this is the sort of thing that happens here. So you bundle up the state of the application, the configuration, the operating system image and so on, you put that into a container. You can then treat that as a unit and try and manage it as a single unit. And this is pretty effective, right? This helps. I guess the question we're asking is, can we do better than that? So we think there's a need to try and disentangle applications from the system, the platforms they run upon. And we can do this if we take the operating system functionality and break it up into libraries and revisit some technology that certainly in the research community in the late 90s was common, which was library operating systems. So rather than having the operating system as this monolithic kernel, you split it all up and you take only the bits that you need and you link them against your application. And you can then target different platforms with the same code base simply by linking in alternative implementations of these system libraries that you're depending upon. So hopefully that's motivated unikernels a little bit. Too much complexity, too difficult to manage it all. Can we do better than containerization provides? So I'll talk a bit now about what unikernels are. I will hopefully have time for questions at the end, by the way. But if anybody's got any quick questions as we go, do please put your hand up and ask. So what's a unikernel? A unikernel is a specialized virtual machine image that's built from a modular stack that adds system libraries and configuration to application code. So it's the entire software stack that you're running upon to the largest extent that we can, all bundled into a single application, a single binary image. This gives several benefits. So they're self-contained. So this simplifies deployment and management. You don't have separate configuration files. Everything is compiled into the image. They're compact, right? These things tend to be quite small, certainly a lot smaller than a typical Linux VM image would be, right? You're measuring them in kilobytes or megabytes, not in gigabytes. They're efficient. Because of the size of them, you can fit many, many more of them onto a single host. And they're portable. As I said, by changing the system libraries you link against, you can target to different platforms very straightforwardly. So in pictures, the aim is to capture the system dependencies in code and essentially compile them away and keep compiling and linking until all the dependencies have been met. So if you consider on the left there, the white boxes are the different components you might expect to have in your application. So you've got some configuration, you've got an application, some application code. You've probably got a language runtime of some sort. You've then got all the services that the operating system provides, maybe kernel threads, processes, all these other features. And the idea is to take all of that, run it through the compiler, and the output should be this single image, right, that's got your application code and the runtime and any of the libraries that are necessary to support that. And that's what we call a unikernel. You do retargeting simply by recompiling. So the development process is quite nice here. You can develop your application using Unix, right, in a standard kind of development environment. Use GDB, use all the other stuff that you'd normally use. The only thing you've got to be careful about is which libraries you depend upon. But if you exercise a bit of care there, you just develop on Unix. You can then flip a flag on the compiler. In fact, you change an environment variable. And you start to link against the Mirage system libraries instead of using your platform, your operating system kernel, to provide networking and things. You begin to use our user space libraries instead. So you can test that everything works as you expect. You then change the flag on the compiler again. And this time, when you compile the application, you won't get a binary that you can run on Unix on the POSIX platform. You'll get a Xen VM image that you can boot onto Xen. And then because Xen provides this nice stable ABI, you can essentially recompile again if you recompile on the ARM platform, and you'll get something that will run on Xen on ARM instead of something running on Xen on x86. And there are more things that we can shim in there at the bottom, so more options that are available there. We simplify the memory layout that you need here because you don't have to support multiple applications running in the same address space. You've got a single appliance with all the code built into a single address space image. So we can simplify a lot of things about how that gets configured and how that operates. So the workflow is straightforward. So you do Mirage config.ml file --Unix, and that says build this for Unix. Once you've configured it, it's the usual, cd to the source directory, make depend if you must, make build. And once you've done that, reconfigure, Mirage configure config.ml --Xen, and then cd app, make depend, make build, and the output has changed. Okay, and you can now boot that output. The idea here, or the technology here, is that everything is happening via the OCaml module system. So we're using the power of the OCaml module system to feed in alternative implementations and have the compiler check for us that they're going to be valid, that they're going to fulfill the necessary type signatures. Before I go further into this, who has programmed in OCaml, even if you've not used Mirage? Okay, who's programmed in Haskell? Any other functional languages? Scala, maybe? Yeah. Java? Well, no comment. Okay, so I'm going to talk a little bit about OCaml now and try and go very briefly through some of the syntax involved. If you don't follow all the details, don't worry about it. There's loads of resources on the web for doing this. What I'm going to try and do, though, is give a flavor for how we use the module system to satisfy type signatures, to make all this kind of work in practice. So in Mirage, what we've done is we've taken all the system components that you normally expect to find in your operating system and restructured them as modules. What that means in practice is that we've got a collection of module types, so type signatures that define and describe the structural shape of each of these components. So they say what types are expected to be contained in a module, they say what operations are expected to be available in a module. And then we've got a set of independent libraries which satisfy those signatures, so they implement those types. And then the build process, essentially, the configuration and build process works out which of those libraries you want to have included into your application to satisfy those types. And because it's all expressed in the type system, the compiler can tell you, you forgot to include something that satisfies the TCP signature, so you're not going to be able to do that. So you need to find a TCP library that's going to work on this platform. We use them everywhere. So we've got full implementations of a network stack, including a TLS stack in OCaml. It's a nice flexible approach, so you can do lots of layering in crazy ways if you wish, using these signatures. And then we have lots of different implementations of module signatures. So if you want, you can implement all these in JavaScript. You can use the JS of OCaml compiler, take the OCaml code, and build it to run in a web browser. Also supporting Xen, Unix, and then an increasing number of other platforms. So writing a component turns into, essentially, a component is a module that implements a particular type that we support, a particular module type, and it has very limited dependencies. And in particular, it depends just on other Mirage module types, generally speaking. One of the nice things about the module system in OCaml is that you can parameterize modules by other modules. So in the ML world, this is called a functor. This is essentially something that maps modules to new modules. This is not the same as what Haskell people call a functor. I have no idea why this should be the case. Functional programming people do this sometimes. You can think of them as a type-safe version of C++ templates. Okay, so you can fill in, you can parameterize these things with other modules that you've got to hand. So for example, the device type in Mirage, it's a module type called device. Its signature is it expects to have some parameterized I/O thing available to it. It expects to have a type representing a device available to it, T, and it expects to have a type representing an ID for a device. And then there's two functions in that interface. One returns the ID given a device, and the other disconnects the device and returns some kind of empty I/O. Similarly for flow, so for some kind of generic flow type, you expect to have something representing I/O, parameterized type representing I/O. So that's alpha I/O, is that how that's pronounced? You have some type that represents a buffer, and you have some type that represents a flow. Then you have the usual sort of operations, read, write, and write v, that take flows and produce buffers or consume buffers. You can compose these things together, right? This module system is very compositional. So if you want to define a type that represents a TCP/v4 device or thing stack somehow, you're going to need to provide some type representing a buffer, something representing an IP device, something representing an IP address, something representing a flow, and then you're going to say, and this thing can be treated as a device if you think of the ID as being the IPv4 device it sits upon, and you can treat this thing as a flow. If you think of the I/O type being the same as the I/O type that you've got in your flow, you think of the buffer being the same as the buffer type, so the buffer types have to be compatible here, essentially, and flow types have to be compatible. So you can compose this flow and device together and produce this sort of TCP/4 thing. If you go and look at that interface file, that exposes all of the types that Mirage relies upon. So all of these different structures that we're willing to support and that the libraries we've got implement. You then take this abstract type. So that had a bunch of abstract types in it, right? This was, I didn't tell you what a flow was, I didn't tell you what a buffer was, I just said they had to be the same between these two things. You can then refine this into concrete instantiations. So you can say that a flow, the parameterized I/O type alpha I/O might actually be a parameterized lightweight thread, so a particular user space threading library we use a lot in Mirage. And the buffer would actually be a C-struct buffer. So this is giving some concrete instantiations of these things. And so you're taking this abstract type and now saying, okay, this is the real thing that's actually going to run. This is what's going to happen in practice. And by expressing all of this, again, the compiler can check that everything is matching up and that you've not forgotten something. So, very brief introduction to functors there. I'll try not to get any more technical than that, because frankly, it gets weird and I don't fully understand it all. I'm not an FP person. So, a Mirage component usually contains code parameterized by functors with very limited dependencies, and in particular, no platform dependencies. We try and avoid taking implicit dependencies on the platform. And a collection of libraries where the functors are applied that make things suitable for interactive use. So we've got this separation, we've got this breakdown of the monolithic kernel into all these different pieces. So what then happens when you go through that configure and build process? You might start out with an application that needs to provide the application signature. And if it provides this app signature, this diagram's a little old, I'm afraid, so some of the terminology is slightly different now, but the ideas are still the same. So if it satisfies the app signature, then that's going to be something that can be run as a Mirage unikernel. Right? And that will be something the compiler can either build and link for Xen or something it can build and link for Unix. To do that here, it needs to have an HTTP server. This is your homepage app. That's not unreasonable. It needs something that satisfies the HTTP server signature. And in this case, it's going to get that. This is the development cycle. So you're still building on top of Unix, very standard kind of environment. You're going to provide that using the co-HTTP library, which provides the HTTP signature, satisfies that signature, but it needs to have a TCP stack. It expects to have a TCP stack available to it. And in this case, that TCP stack is provided by the Unix socket library, which itself depends on the Unix elf library. Okay, so this is the dependency chain of all the libraries that are necessary that must be available for your app to be able to run at the end of the day. So that's development. What you can then do is you reconfigure it and say, actually, I'd like to start using the user space network stack. So rather than fulfilling the TCP dependency for co-HTTP with Unix socket, I'll fulfill it with Mirage TCP. Okay, so this is the Mirage TCP stack now. It fulfills the same signature. The compiler can check that that all works, so it comes out there. And that depends on the rest of the user space stack. So it depends on Unix TUNTAP in this case for access to the raw device. And once you've satisfied yourself that all works, you do the reconfigure step again. And now, instead of at the point where you're looking for the Mirage network stack and you want to find, it provides an Ethernet interface and it requires some kind of network device, some netif. Instead of satisfying that with Unix TUNTAP, you can satisfy that with a pile of Zen libraries that give you access to devices through Zen. So simply by linking against these other libraries, again, all type checked all the way through, by linking against those libraries, you get something that's going to be a Zen virtual machine image. In the interest of time, I won't go into this in too much detail, but this is kind of a fragment of the OCaml code that you end up writing. So this is your sort of server code, if you like. So here at the end, you're calling the HTTP server constructor, if you like, with a configuration. And the configuration has two functions. One is a callback function, which says what to do when you get a request coming in, and one is a connection closed callback, which says what to do when the connection closes. Notice that this module at the top, module main, is parameterized by 3 other module signatures. So what that says is that I expect to have passed to this thing something satisfying the console signature, something satisfying a read-only key value store signature, which is the kind of the ropey storage system we use, and something satisfying an HTTP server signature. So that's kind of concretely what this looks like when you write the code. So you can then deploy this in various different ways. You can say, I want to fulfill these signatures with various different background libraries. It might be as a Zen unikernel with all the data built into the image, which is essentially what's running on our website currently. It might be reading data dynamically from a block device. It might be as a Unix binary, etc. So you can fulfill these things in different ways by picking different combinations of underlying libraries. You express all that using a configuration language, which is an embedded domain-specific language inside of OCaml. So the top there, you build a web server that's going to listen on TCP port 80 in this case. You build a job, so what was an app on the previous slide, called slide deck, and you say, well, this is the signature this expects. Right? This is going to expect to see a console, it's going to expect to see a key value read-only store, it's going to expect to see an HTTP server, it's going to produce a job at the end of it. And then you actually create that, you actually instantiate that at the entry point, let unit equals. And you provide concrete instances of things that satisfy those signatures. So you have slide deck is this kind of job. Default console is the standard console that satisfies the console signature. FS is a variable that's not shown on here for reasons of space, but that's going to be essentially the file system, the data you expect, which is going to export this KVRO signature. And then server is the HTTP server that you've built up at the top. So there's this direct correspondence between the configuration code you've got there and then what looks in the application code, the server code that you've written. Code generation then takes place through the MIRAGE command line tool. This is what the configure step does. It takes that configuration expression and turns it into some actual code that the compiler is going to make depend and make build on. So in this case, this is the sockets, the Unix sockets library. So this is kind of the lightest weight one. So most of the, all the networking, for example, is devolved to the Unix kernel. On Zen, you don't have a networking library. Right? You don't have a networking in the kernel. So you have to build this up yourself, and you do that, or rather the compiler does that for you because it knows about these signatures, by starting out with a network interface and making it into an Ethernet interface, taking an Ethernet thing and making it into an IPv4 thing, taking an IPv4 thing and making it into a UDP thing, and so on. And that essentially gets exposed then in that auto-generated code as stack v4 thing. And then everything else is the same. So this is sort of under the hood what actually ends up happening. So in summary, UNIKERNEL is a parameterized module. It's parameterized over its dependencies. We use OCaml functors to separate the functionality into modular chunks, and Mirage provides a large library of these types that can be assembled to produce different outputs. And we manipulate these through metaprogramming. So you write this configuration file that's used to generate the necessary code based on how you'd like this particular, how you'd like to compile this particular time. So what's the end result? Basically, good, as you might expect. That's what you'd expect me to say, right? So the appliances that you can build with this are pretty small. So we're talking hundreds of kilobytes, maybe megabytes, rather than gigabytes for a full-featured image. So we have, these figures are a little old now, but we have a DNS server, we have a web server, we have an OpenFlow learning switch, and we have an OpenFlow controller as well. This means the boot time is very good. So this is comparing Linux, power virtualized on Zen, booting versus a Mirage images booting. So we can boot both with less memory and a lot faster, primarily because there's so much less memory. We also looked at some macro benchmarks, so we tried to see how does this perform in practice. Is it actually going to be usable for some of these system-level services? Probably the most interesting one is the DNS server. So the baseline here is running bind9 and NSD, which is a higher performance DNS server, written in C on Linux. So NSD bind is a bit weird. NSD is pretty good. That's sort of consistently just about 67,000 to 70,000 requests per second. Is what this thing is serving. So when we did the first version of the Mirage implementation of this, it wasn't so good. We're looking at 40,000-ish there, which is not too bad given it's all on a camel. We weren't that disappointed, but on the other hand, it's not good. Right? It's certainly not competitive. But taking a look at what the code was doing, it turned out that we could add, it was about a 6-line patch to memoize output DNS response packets. So just essentially to stash them away, and then when you're going to respond for the same query, you can take one of those packets, twiddle the fields to be the appropriate destination address, the appropriate checksum, and all the rest of it, and send that packet on its way. That was a 6-line hack, and it doubled performance roughly. So we got up to 77, I think, thousand requests per second. And it was a relatively straightforward hack to do because you were in this very high-level language to express all this. It probably would have been a lot more invasive to go and try and do that sort of thing in a standard kind of C-based application running on top of a kernel, to take the serialized output packet, memoize it somewhere, rewrite it, and so on. It could have been quite difficult. Just in case you're thinking that if we did it in C, it would just go faster because it would be in C, it turns out that the effect of user space networking libraries, for example, in C, vastly outweighs any language difference here. So if you had sufficiently good user space libraries, perhaps you'd see some benefit there. But in practice, LWIP, which I think was the networking stack we tried to do this with, it just doesn't perform well enough to counteract that, to balance that. Very quickly then through this. So in terms of scaling, the OCaml runtime is currently, although it's being worked on, is currently single-threaded. So we scale by running multiple instances of a server rather than having a server that uses multiple CPUs. But this actually turns out not to be too bad because you end up scaling by running lots of instances and you don't have to pay for thread-level interlocking. So in some sense, this seems to be okay. This is not too bad a trade-off to make. And then finally, the OpenFlow implementations we had were not brilliant, but they were sort of comparable with C++ implementations. They were certainly doing a lot better than I think Maestro's in Java implementation. So hopefully that's given some idea and not completely bewildered everybody about what unikernels are, okay, and how they work. So what I'll talk a bit about now is how we can use them, what some of the other benefits are. So one observation we made, a lot of network services suffer, they get worse as latency increases. Things like Siri, Cortana, Google Glass, and so on. So we're thinking, okay, well, can we move computation closer to the data? If we can do that, we can reduce latency. Right? We have to move the data less far, things should go quicker. A lot of security problems was part of the motivation for this. So lots of security problems, particularly going into embedded devices, IoT devices, where they've not had maybe as much work put into hardening them. So can we put some network protection in the way? Can we do something to assist people when they start to deploy these devices to make them a bit safer? So we call this just-in-time summoning of unikernels. Essentially, what we can do is we observe that because we can boot these things so quickly, we can actually boot a virtual machine to interpose itself on the path between the client and the service that's being accessed in the time it takes to do that round trip, the time it takes to create that connection. So this needed 3 things: performance improvements to the boot process and tool stack in Xen, shared memory communication between unikernels, and then this directory service. This is the basic architecture. So the idea is you've got legacy VMs sitting protected, right? They're not directly network accessible. They have no connection to the network at all. The only thing they can connect to is this shared memory communication channel. And the idea is that when traffic comes in, we can boot a unikernel in response to that traffic that will handle that traffic, that will deal with that external connection. So there's nothing there really to be attacked, right? It doesn't have a bash shell. Shell shock doesn't exist, right? It's a unikernel. And it can communicate with a legacy VM through this shared memory channel. So you've got this kind of legacy VM specific firewall, if you like, that's been interposed. There were a variety of improvements we had to make to achieve this. So removing libc, for example, from the tool stack, avoiding hardware emulation. This was quite good on ARM because ARM is a lot simpler, doesn't have all the legacy stuff Croft associated with it that x86 does, and doing a lot of work on the boot process itself to deserialize it. A lot of things in the Xen boot process were quite serialized, so it just took a long time because you're waiting for things too much. So making things run more in parallel helped there. So this improved a lot of scaling problems and reduced the boot time significantly. The second thing was this shared memory communication channel. So this is called CONDUIT. So this is zero-copy shared memory. You essentially share pages between VMs, and you do so using XenStore as a rendezvous point. It hooks into high-level services like DNS. It's compatible with the vChan inter-VM communication protocol, for those people who know that. Too much detail, not enough time. The final thing was the directory service. So this is essentially performing the role of inetd. So when a name resolution request comes in, JITSU looks at that request, and either it can hand things off to the unikernel that's already running, or it can start a unikernel booting to provide the service that's named by that name request. And then it can return the endpoint that that unikernel is going to have. It also acts as a proxy until that unikernel has finished booting. So we can mask a bit more of the latency by essentially completing the TCP handshake while the unikernel boots, then handing all the state of that TCP connection off to the now booted unikernel to pick up and continue with. So this is a picture of what's going on. So the query comes in, JITSU can start the domain being booted, it can respond with an answer, and then while the domain, the unikernel on the right there is actually booting, JITSU is handling the SYNAC process with TCP and writing all that information into XenStore. So then when the unikernel finally finishes booting, it can pick up that state from XenStore, and it's got hold of the connection, and it can now start serving the connection correctly. So you're buffering requests into XenStore and then replaying them into the unikernel after it's booted. The net effect of this is that on x86, we can get boot times down to around 30 to 45 milliseconds for a unikernel to come up. On that QB-board 2 ARM device, we were looking at less than half a second, so 300 something milliseconds. This was quite a lot faster than the other things we could compare against. So you can boot these things in the time it takes for the TCP connection to set up. So you can do this very dynamically if you wish. The final benefit I mentioned was about being able to store these things in Git. So, for example, the Mirage website, we've been dogfooding this for about 4 years now, so the Mirage website is a Mirage unikernel. Okay? The development process for updating the site is that source code updates get merged into the GitHub repository. So you send a pull request, Travis build kicks off, checks everything's good. Somebody on the team then merges that into the repository. That kicks off another Travis build. When that build is successful, in particular when the Xen version of that build is successful, the unikernel gets pushed into another GitHub repository, the Mirage deployment repository. And then it's a little bit hacky at the moment, but there's a cron job running on the deployment server that has a post-merge hook in that repository, so it just keeps pulling from that repo. When there's something new, the post-merge hook kills the current version of the website, boots the new version. So all the actual compilation of the website is done using Travis resources. And then the output is committed back to another GitHub repo. So we've got the full history of all binary versions of the website that ran. So everything is version controlled.
Do you have reproducible links so that you can actually check that Travis is not modifying the files?
We don't have that at the moment, other than diff. Or comp, I guess would be better. But that would be something you can build. Because it's all logged in Git, you've got the information you need. So implications of this. Historical tracking of source code and binaries in GitHub. So you can do Git tagging, you can do Git log, you can Git pull to get a new version deployed. Checkout to go back in any time and point. If you wanted, you could try and do something with Git bisect to pin down deployment failures. Okay? There's a lot of power that you get by having this complete history available. Low latency deployments. So you don't need to wait for your distribution to pick something up. You just pull the new version. And when it arrives, it boots and you're done. Single development environment for cloud and embedded environments. So you can write it once, develop it on Unix, develop it on a laptop, whatever, very convenient. Change the compilation environment and you get a different output, but the same code is there. And then it's highly responsive deployment for legacy services. So the DNS server interprets, for example, commitref.service.name, and it can check out that particular revision and boot that version of that service that you wanted. And it can do all that while masking the latency, so this can happen in real time while clients are trying to use that. So that's kind of all the technical stuff I'm going to talk about. Last couple of minutes, we think this is a good idea. We'd like to see more people using it. Please talk to me if you'd like to. Or just pick it up and give it a go. There's a whole bunch of other stuff that's been built to try and enrich this ecosystem. So we've got something called Ermin, for example. This is a Git-like distributed branchable storage. So this is something that's accessible programmatically from in your code, as well as if you choose to back it with the file system using the command line tools for Git. So you can, I've got, for example, at the moment we have a prototype of an ARP stack that we had a few bugs in it, so we thought, okay, it needs to be rewritten. And that's been prototyped to use Ermin to manage all the state in that. So while you're debugging this, you can do git log and you can see all the transactions that took place in the ARP stack. You can see the timers that went off, the state machine transitions, and so on. We've got OCaml TLS, so this is a from-scratch native OCaml TLS stack. We've got C types, so this is modular C foreign function binding, so if you need to pull in some legacy code, you can do that and expose it in a pretty principled way. And there's a profiling toolkit that's been introduced and is being improved quite rapidly. To say a bit more about TLS, since that's quite an interesting one, this was begun in January 14 by David Kaloper and Hannes Mennert. It's a full re-implementation of TLS, including X509 and all the ASN1 baggage. The functional style means the same code, so the same library code is used to do trace checking from the live site. So we've got a live site running, HTTPS TLS openmirage.org, which if you connect to will give you a breakdown of actually the TLS handshake that took place. Traces from that bit can be collected, PCAP traces can be collected and played back through the library to do verification and compliance checking. And if you've I don't know if they've closed it, they might have closed this now, but for a while we had a pinata, so there was a Bitcoin pinata. If you could break the TLS server, then you could keep the Bitcoins that you'd find. Nobody did, that we know of. And there's other stuff going on. So we've got IMAP client and server, we've got an SMTP server, XMPP communication is coming along, multicast DNS, IPv6. There's quite a lot of stuff happening, quite a lot of stuff building here. I said at the start, I mentioned Nymote. So this is technology we are using to try and rebuild a software stack so that more people can play on an even playing field, if you like, in the internet. So you can run your own services. More normal people can run their own services without being dependent on all these large cloud companies to do it all for us and to kind of own us in the process. So we're trying to build this technology to build personal clouds, essentially, so that you can actually run this and contain this and manage this yourself securely and enabling you to interconnect and synchronize between personal devices. I've talked a lot about Mirage, obviously, because that's the project I'm involved in. It's not the only UNIKERNEL platform out there. So if you don't fancy OCaml, but you'd rather do Haskell, then there's Haskell VM. Rump kernels coming along, OSV in Java, I believe, ClickOS if you focus on routing. So there's a growing number of these types of these implementations, this sort of technology. It's kind of componentization and reassembly, it's modularization. Lots of different scenarios in which it's being used. And the performance is not too bad and can probably be improved further. There's probably still quite a bit of room for optimization there. So, there we go. Thank you. Any questions?
So you've shown that you have an abstraction for TCP/IP stacks and networking and things like that. Do you also have abstractions for block devices or graphics devices and things like that? So how vast is the ecosystem for these?
So block devices, yes. Graphics devices, nothing specific that I'm aware of.
So you could actually have some stuff like databases and stuff like that. So building a kind of full-featured web server is possible. So.
Yeah. As I said, so our web server, I mean, that URL there has been running for about 4 years using this technology, obviously improving over time. But
if you deploy the static content with it, right? Than if you would take user input and save it somewhere.
Oh, yeah. And I think particularly with Ermin now, that's quite a nice tool to build on top of that. We don't have, as far as I'm aware, nobody's built a sort of a SQL-like interface to that. It's a Git structured file store, but that could be done. That's something actually we're interested in having done in the next few months for another project. So if anybody wants to engage with that, talk to me, drop me an email. Any other questions?
So typically, when you work, for instance, on Android development or on iOS development, and you run it in your simulator on a different stack, it behaves differently, especially timing-wise. So how you mitigate that so that you can ensure quality when you deploy it to the actual SEN production environment?
That's an interesting one. So we don't do anything explicit about that at the moment. On the other hand, for networking in particular, we've got quite a lot of things going on which are aiming to build much better tools for testing and debugging the network stack. So one of them is better ability to control time, virtual network interfaces, so you'd be able to play with different timings, for example, and maybe see how things were behaving and tracing there. But that's quite a lot still in development. I've got a postdoc at the moment who's just finished doing an Isabelle proof of BPF, in fact, so that we can do trace generation based on a proven BPF stack. So there was a question at the back.
On the last slide, you had an interesting link to a talk. So what wouldn't you use this for? What wouldn't you use the UNIKERNEL for?
I would use them for everything. They're great. Go and watch Adam's talk for an alternative view.
requires you to have user space, so ring 3. Would you want to put this unikernel in ring 3?
The answer is almost certainly yes, but we haven't done details of that yet. It's something we're going to look at, though.
What are the things that you have to do if you want to target a new platform? So you have to write a new OCaml runtime and provide these instructions, or what exactly does it involve?
Typically, you've got to take something that represents your platform and map OCaml runtime onto that. Often, there's not very much you need to do because so much of the libraries that we have are written on OCaml that once you've got the baseline there, a lot of it just automatically falls over. So you may need to think a bit about memory, for example, how you've managed memory. You may need to think a little bit about it's like a basic sort of timer interface, things like that. But it's a fairly narrow interface at the bottom there. And then a lot of the rest of it just falls over because it's all in the high-level language anyway.
Are there any larger projects with this in production, like commercial stuff? Or?
We've had some interest in people doing that. I'm not aware of any large-scale deployments that are using it in practice at the moment. The OCaml language is certainly used for a variety of large-scale deployments by other people. So, in some sense, we're investigating that with some partners, but we've got nothing actually fully in production yet that we're aware of.
And you mentioned that Zen is quite an important platform for you. Do you also support KVM, or do you have backend KVM?
We don't explicitly support that currently, but that would be something that we're interested. Again, that it's possible to do, right? It's just we haven't had time to do that. We're interested to do that ourselves. Okay.
Okay, so thank you very much again.
Thanks.